Today, for the session, the cosmology one, we have 4 talks before the tea break. And the first one is by Albert Stebbins. Albert.
Okay. Anyways, I'll start out with the claim. One is that white noise inhomogeneities are continuously generated on large superhorizon scales, inevitably. And in standard cosmology, this white noise will be the dominant inhomogeneity on the largest scale. The amplitude depends on stuff, and it might be too large to see, but it should be there. And I'll start out with talking about the flatness problem, which you all know, which is basically we measure the omega naught, the density in terms of the critical density. It's very close to 1. Measurements give about 0.05. And if you extrapolate that back to, say, the latest time when inflation, when with the standard cosmology sort of had to work, which would be sort of the time of BBN, that number would be 10 to the minus 20. So why is it so small? Okay, well, that's one flatness problem, but we don't actually see the entire universe. We don't really know what the mean density is. We only see our local patch of the universe, which is about 10 gigaparsecs big. And you can write down exactly the same thing, but sort of the inhomogeneous omega, which we measure with things like the CMB, and we find it's about 10 to the minus 5, a bit smaller. And if we go back to BBN, that number goes to 10 to the minus 24. So how do you explain this 10 to the minus 24? And the reason it's hard to explain is that in normal late-time cosmology, the universe is gravitationally unstable, and that's why it grows so much. So takeaway point, the universe is unstable. Any sort of little jiggle can make things happen. So the standard explanation is that there was a period of early inflation which drove omega equals 1 because the equation of state was different. And so the linear, and also we have that inflationary epoch produced approximately Harrison-Zuldovich spectrum of perturbations. You can write that as sort of the average, the RMS deviation from 1 of this local omega, and it goes like volume to the minus 2. And it has a particular dependence on time. So all of those things I agree with, large scale inhomogeneities grow just like that. So the thing I have an issue with is that linearity keeps the evolution of different wave numbers independent. Now, I agree with the statement that if linearity was true, the different wave numbers would be independent. But my problem is that I think things are coupled inevitably. And therefore, on larger scales where omega is very small or very close to 1, it couples to the very much smaller scales where omega is much bigger. And this would cause the larger scales to become inhomogeneous, and the instability would kick in, and you produce large-scale superhorizon perturbations. No, there's various arguments that people have made why this coupling cannot be there. I won't go through all of them, but one argument is sort of based on the conservation of momentum, which prevents matter from like spontaneously moving. To get out unhomogeneity, you need 2 pieces of matter to sort of come close to each other, and that would be prevented by the conservation of momentum. But let me give you a little physical model of the universe. Suppose this is the universe, or a patch of the universe. It's this, there's gravity that points down, and it's this cone. And if it was perfectly balanced in a completely isolated system, the universe is isolated, there's no external universe it's connected to, we believe. If momentum was conserved and it was perfectly put vertically, even though the atoms in that cone were jiggling, the thing would never, ever fall down. And the standard picture of cosmology, that patches of the universe are not quite vertical, but they take a long time to fall down. But another possibility, which isn't usually what we think of, suppose the interactions of the atoms didn't conserve momentum. There'd be two reasons why that thing would fall down. One is that it wasn't aligned perfectly, or two, that the jiggling of the stuff that didn't conserve momentum would give the thing momentum and it would fall down. And that is what I'm claiming is an issue, is that there is this non-conservation of momentum which causes things to fall down perhaps earlier than you would think. So what is momentum? So we like momentum conservation, and the reason we like it is because we think we live in Minkowski space, or something that's a regular homogeneous universe where you have an isometry. You get spatial translation isometry, and that gives you the momentum conservation. But we know that there are the space-time is not Minkowski space, or it's not FLRW. It has small inhomogeneities in it. And therefore, momentum is not conserved. In fact, there are no conservation laws because there are no isometries for the space-time we live on. But the deviations from FLRW are small. But like we say, it's an unstable system. And if a little bit of momentum non-conservation could cause things to happen at a much, much later time. So basically, if you assume linearized dynamics, which people almost always do in modeling the inhomogeneities in the universe, you will get linear momentum, and there'll be conservation of momentum, and things will only fall down due to initial misalignment. But if you include nonlinear dynamics, the fact that there are no isometries, momentum is not conserved, and that cone will fall over perhaps sooner than you think, even if it was perfectly aligned. So this is actually a representation of a very general phenomena, which I call the universal large-scale white noise, or the large-scale white noise theorem. And it's sort of trivial to show that suppose you just had one quantity, it evolves according to a nonlinear homogeneous in space partial differential equation, and it had initially some sub-Poissonian spectrum, i.e. P of k of that quantity q goes to 0. Then, if there are any nonlinear terms that are not conservative, then you can calculate p double dot at 0k, and it's positive. So immediately, the longest wodes will start developing this, and because p goes to a constant, generally speaking, p will go to a constant at very large scales, very small k. You'll get a power spectrum that's white noise. And to give you an example, this bottom thing is the most general homogeneous second order partial differential equation. Of course, the equations that describe GR are not second order, they're infinite order. They're not described by a Taylor series. And this is another reason why white noise. I'm not claiming that causality is the problem. So causality says you can't produce correlations on large scales, which I agree with. But that doesn't mean you can't have you need to have zero power at large scales, because white noise has zero correlations. So basically, the small scale jiggling, these nonlinearities produce white noise on the largest possible scales. So it's sort of this interesting connection between small scales and large scales. And so I've been talking sort of qualitatively about this, but you can actually do this. There's a bunch of equations here. There's stuff we call curvature perturbations, which was very closely related to this omega naught, or this omega quantity I talked about on the first page. And it's basically, you can define a quantity which is 8 by g rho, where rho is the density in the center momentum frame. And theta is basically the rate of expansion of the center momentum flow. So that's what I call K, curvature with a K. It's closely, see if I can do this. I'm pointing it the wrong way. It's closely related to this script R people use in gauge invariant perturbation theory. But you want to use K and not R. And the reason that you want to use K is a locally defined quantity. You could measure it in this room or anywhere, and it therefore obeys a PDE. R is like a gravitational potential. It's not locally defined, and it doesn't obey a PDE. So that's why this theorem I talked about applies to K, but not R. And you can write down the exact equation in GR, where sigma is the rate of shear of the flow of the center momentum velocity. Omega is the rate of rotation, and U dot is the proper acceleration. So this is an exact GR expression that people like George Ellis use to formulate what they call covariant perturbation theory, which I think is actually a more physically understandable representation of cosmic inhomogeneities. And you can show that on large scales, if you do averaging, that K will evolve according to this equation, the first and second order. Basically, on large scales, K goes as a squared, or 1 over 1 plus z squared. And in the second order thing, if you start out with it evolves according to the average shear minus omega squared minus a squared, where alpha, this is the proper acceleration. So there's a bunch of terms, but remember, if we do the power spectrum, we square that. So the signs here don't really matter. Unless there's some weird cancellation, K will develop this large-scale white noise I'm talking about. So any sort of shear, vorticity, or proper acceleration on arbitrarily small scales will lead to white noise on arbitrarily large scales. And so that's sort of the large-scale white noise phenomena that I talk about. And like I say, up to this perturbation theory, these are exact equations. There's no funny gauge issues or anything. And these are all locally covariant quantities. If you were at Fermilab, you would say you could talk about this as a scattering problem of high momentum modes to low momentum modes, but this is not Fermilab, so I'm not going to dwell on that. So basically, like I described initially, the flatness problem is exacerbated by these nonlinear effects. So in order to obey the observations, you have to arrange for the small scale wiggling, the omega, the shear, the vorticity, or the proper acceleration to be small enough to not be in a disagreement with the observations that K is very small on large scales, or omega is very close to 1. So this is sort of a semantic thing. It's confusing because I'm saying you're in the linear regime, but nonlinearities are important. So linear is like when the variables are small, things are very homogeneous, but nonlinearities are any effect of the nonlinear terms in the equations, even if you're in the linear regime. And nonlinearities will dominate in linear cosmology. So this is not a contradiction if you define your terms right. Okay, so there's another theorem. I mean, cosmological systems are often self-similar. Not exactly, but in some limits. Like, for example, in the matter era without a cosmological constant, and if you have a flat universe, then that's a self-similar system. Gravity doesn't introduce any scale. Similarly, in the radiation era, since the speed of sound is proportional to the speed of light, that's also a self-similar system. So that general partial differential equation I talked about reduces to this and described by 7 numbers. But anyways, if you take this general thing, you can develop what you call the no scale theorem, which basically says it's physically inconsistent to have no scale, meaning it's physically inconsistent to have a self-similar equation of motion and a power law spectrum. So that means like the Harrison-Zoldovich idea does not work. I mean, we don't believe Harrison-Zoldovich works on all scales, but this is a new reason where it has to get cut off. It can't be a power law down to arbitrarily small scales because the nonlinear terms would be infinite. There's another approximation we call the leading order Born approximation. You can sort of figure out by the name. You can combine that with self-similarity. You can do like, I can't do real simulations. I can only do 1D simulations. So like this, not like that. But anyway, so here's an actual a simulation of the power spectrum of using Newtonian gravity because it's harder to do numerically real full GR. So in this plot, the linear theories in red. So there's a time sequence. Here's the power spectrum. So it's Newtonian gravity with a constant sound speed fluid. The exact solution you can write, is the orange thing. And this approximation is the blue thing. And you can see that initially they all sort of agree, but if you go to late times, you get this white noise tail, surprise, surprise, on very large scales, very small k. So this is a power spectrum versus wave number. And that this leading order Born approximation, which you can do analytically, is a pretty good agreement with the exact solution. So anyways, we have this phenomenon and we found a good way to numerically determine its amplitude. So here's like a close-up of like the last thing. These two, the Born approximation and the exact solution agree pretty well, but on large scales, they're completely disconnected with the linear theory thing. Okay, 0 minutes. So you can do, you can add white noise to your lambda CDM model and try to constrain it. You can show that adding that extra parameter doesn't really change the contours for any of the other parameters. And there's just some limit on it. Basically, the large scale white noise cannot dominate on scales below wave numbers below 0.73, or has to dominate on scales, whatever. It's equal to the lambda CDM thing on 10 gigaparsecs or a few gigaparsecs scale. Okay. And you can sort of work out the scaling. I guess I have 0 minutes, but basically here's Harrison-Zoldovich, k to the 1. Here's your large scale white noise. And this is where, the largest value, this is where they'd have to meet. And so I have 0 time left. So I'll just say that what this means is you have to cut off a Harrison-Zoldovich-like spectrum on 1 co-moving parsecs in order to avoid producing too much white noise on large scales. And you can work that with our analytic approximation. And it's a general thing. You don't really have to do any simulations to figure out that scaling. If you don't like this, I would say don't cry over spilled milk. This small scale stuff is going to spill into large scales no matter what you do. All right, thanks.
You can have probably one quick question. Sorry.
So as you say, this point of view is quite controversial, and I can't evaluate the pros and cons, but perhaps you can tell us, for the people who disagree with you, Do they disagree on the mathematical formulation that you presented or just on the interpretation of the formulation?
I think they disagree on historical precedent. I mean, because I'm doing things not the way in this covariant perturbation theory, it's not a language a lot of people understand. But it's actually, I think
But they do understand that you should be able to get the right answer from different gauges. So that part of calculation, the community understands.
Well, I guess they think I did it wrong or something. I don't know. But it's a very general phenomenon, so it shouldn't be surprising. Say it again. Yeah, effective field theory. Well, I mean, in order to get this right in the real universe, you need to do things over a dynamic range of 10 to the 10 and to an accuracy of 10 to the -5. So effective field theory doesn't aim to do that well over those large scales.
Very good.
I just wanted to thank you and say your talk left me very gruntled.
Was very what?
Talk left me very gruntled.
Okay.
Okay, thanks a lot, Stebbins, Albert. And the next talk is by Glenn.
I think I will do a 5 minutes.
Okay, and do I have 20?
20, yeah. All right, late.
Yeah.
And do I have a clicker or something that will work? Yes. So where is your presentation? Let's find it. Here. So I'm going to go here. It's here. Platform next to you. Yeah. We're gonna pull that and pull that. Right. Share that on Zoom. Share. Go. Thank you. Down. Down. Great. So after that great gruntling talk, I want to present you with another statement that contradicts everything that you learned in kindergarten. And I want to thank Lloyd for teeing it up yesterday. So I want to convince you that we actually have strong evidence that the universe is not, as we've been taught to think, statistically isotropic. And this work I've done with lots of people, especially lately, in something called the Compact, the Collaboration for Models and Predictions for Anomalies in Cosmic Topology. Lots of people. The people in blue are citizens, except I missed Jim Mertens. Oops, Jim Mertens, who is also a citizen and is here in the room. And I want to thank Professor Charles Dyer, who was my undergraduate advisor and was one of the people I saw on some of those lists, and who got me started on thinking about a lot of these issues a long, long time ago. Anyway, when we look at maps like this, as we've been doing for a long time, and even better maps like this, as we've also been doing for a long time, and even better maps like this, which we've also at this point been doing for a long time. The thing all the maps, which even though they don't cover quite as much of the sky, are even, we've also some of them not yet looked at, but others been looking at for a moderately long time. The thing we're taught to do since we went to cosmology kindergarten is to explain them in spherical harmonics. So why do we do that? Those people who are older than me wouldn't have started out doing that. Those people who are younger than me would have thought, no, of course that's what you do. That's what we're taught to do. And the reason is that the standard model for those fluctuations is that this is inflation and the sky is statistically isotropic and the ALMs are Gaussian random variables. And so maybe not quite all, because there's going to be some non-Gaussianity, but nearly all the interesting information is contained in the angular power spectrum. And, we saw Lloyd put up some plot like this, some similar one that shows just how amazingly we do moving forward with this way of approaching the data. And thank you to all the people in here, Dick, lots of others, for teaching us how to do this and just how amazingly successful it is. And all the experimentalists who've gathered that data and, and the theorists and the experimentalists who've analyzed it. Because it's a remarkable success. But shouldn't we go back and check this approximation? Well, or this claim? Because it's not in our likelihood functions when we fit the data, because our likelihood functions don't include violations of this because they're not supposed to. So we have to go and check by using other statistics. So or we just ignore it. So what happens when we do that? And what I'll claim to you is that there are troubles in our isotropical paradise, and that the bottom line is that the universe appears not to be statistically isotropic. And then I'll end, if there's time, with some topological musings, but they're not the focus of this talk, just the focus of most of what I think about these days. So let me start with the first thing. That was really first seen in COBE, and it wasn't pointed out till the fourth year COBE data. Why? Well, because by that time we had stopped thinking about the angular correlation function, because theorists had told astrophysicists, don't think about that, think about the angular power spectrum. But nevertheless, we had these graphs, and people noticed that there's something strange about them, but didn't write down a statistical characterization. And I don't know even if you can tell what's strange about them, because it's not really until a couple of years later that people figured out what was, described what was strange about them in writing and in papers. And you might think, well, why do I care? After all, doesn't the angular power spectrum contain the same information as the angular correlation function? Sure, that's true whenever you do some transform of the data, like Fourier transforms, but that doesn't stop us from Fourier transforming data to look at it in some other representation. Okay? So the WMAP team did look at it, and here's a plot of WMAP data. And the thing you should notice here is not the fact that all of the angular correlation functions, which I'm trying to point out here, but I'll go up to the screen, all the angular correlation functions here disagree with the theoretical angular correlation function. That turns out to not be that statistically significant, maybe a p-value of 0.05 or 0.1. What you should notice is that they all, at least all the ones that are from the measured data or from the part of the sky outside of the galactic plane, are very nearly zero from 60 degrees almost all the way up to 180 degrees. And the ones that reconstruct the full sky, or that use the C-sub-Ls that have been extracted using maximum likelihood estimates at the time from the data, disagree a little bit with that, but still have angular correlation functions that are unusually close to data. How unusually close? Well, the WMAP team put down a statistic to allow them to characterize that. And the answer is, and this is sometime later, that you would have expected this quantity, S1/2, which is the integral of C of theta squared d cos theta from 60 degrees to 180 degrees, to be something like 50,000 micro k to the fourth. And instead, on the cut sky, it's about 1,100 to 1,200 micro k to the fourth. And if you take it on the full sky, which I don't know why you would, because you don't trust the part behind the galaxy, it's about 8,500. And that cut sky value happens accidentally in lambda CDM about 3 times out of every 10,000. And we thought that this would go away in Planck. I think that's what most of us expected. This was just some systematic problem, but it didn't. Exactly the same. And it didn't matter how you subtracted out the foregrounds, you got the same answer. And when they reported it as 0.1% p-value, but that's because they only had 1,000 full plane FFPs. Okay, so exactly the same thing. So somewhere around 0.03% of realizations of the concordance model inflationary lambda CDM have so little cut sky large angle correlations. And most of them do it in a completely different way. Most of those realizations do it in a completely different way than the sky, because the easiest way to get no angular correlation function is to have no angular power spectrum. If the C sub L's are all 0, then you get C of theta is 0. But that's not how the sky does it. The sky does it by having C2 cancel the contributions from C3 and above, and C2 and C3 cancel the contributions from C4 and above, which is very bizarre. Okay. In fact, if we replaced all the theoretical CLs by their measured values, cosmic variance would give us only a 3% chance of recovering so little correlation or particularization. And again, most of those would be much poorer fits to the theory than the current data is. So how do you explain that? There's lots of different ways that I think are silly. And well, inflation can't do that. That's the problem. Okay. Just changing the power spectrum doesn't do that because you still have cosmic variance at low L. You can't get away with that. You can improve the fit, but you can't address the problem. And so it seems to me that you need new physics that correlate C sub L's, and it's almost impossible to get that without correlating ALMs, or it is impossible to get that without correlating ALMs, which is statistical isotropy violation. Now, then you say, okay, well, how should I look? If I'm going to look at statistical isotropy, I should look at things beyond just C sub L's. And so people have used lots and lots of ways. So let me just quickly go through a few of them. One is alignments. So like if you look up in the sky and you see birds flying like this, you don't assume that they just randomly happen to be in this pattern. You say, well, there must be something weird. So how might we look at the sky? So for example, for the first multiple, for L equals 1, we never would talk about A11, A10, and A1 minus 1. We would talk about the direction and magnitude of the dipole. So what about the higher L multiples? And I'll skip how we invented this completely new way of representing data on the sky because it wasn't completely new. This guy who you may have heard of had invented it, or at least used it a long time ago, which is to say that you can write the Lth multiple of the sky as L directional derivatives of 1 over R on the unit sphere. Okay. And so those directions are called multipole vectors or Maxwell multipole vectors. And they are a different way of representing data in the sky that are actually used apparently by geometrologists. So they haven't completely fallen out of use, and we've been looking at them for years now. And so the quadrupole has 2 vectors. You can think of it as a plane. The octupole has 3 vectors or 3 planes. And so if you ask where are those on the sky, and here I've put them on an L equals 2 and 3 map, you see that they're all clustered. They're all clustered here. They're all clustered here in one part of the sky that you can't see me pointing to, surrounded in purple, with the 3 octupole vectors, 1, 2, 3, and the quadrupole vector sitting right in the middle of those, much better in the middle, for actually, if you remember that you're supposed to correct for the Doppler effect. Okay. So again, another thing that shouldn't happen in a statistically isotropic universe. There's another thing which is, people talk variously called power asymmetry dipole modulation. We call it low northern variance for a reason you'll see in a moment. And that is that when you look at the sky, one part of it seems to have more going on, namely the part to the bottom right. And in fact, that's true. The northern sky, if you look at the PDF of the variance of the sky, the southern sky is completely normal, and the northern sky sits here at the point P of about 0.1%. Mm-hmm. And then if you look at the low L multiples, you'll see that that C2 is lower than C3, and C4 is lower than C5, and C6 lower than C7, and that the C2L is less than C2L plus 1 for L equals 1 through 9. And so with so many anomalies, what do? Well, we're trying to write a physics report, but what we want to tell you is that these aren't tightly correlated to one another. Okay? So this was first studied by Hutterer and Muir and Adhikari, and they showed that the statistics aren't correlated, but it's not quite the right question because they were studying the peaks of the distributions, and we're way out in the tails. And what we did is we looked at those tails and we looked at it in all the different Planck maps. And what we found is that the worst that it could be is that the p-value of all four anomalies, and we chose 4 that appeared to us likely to be uncorrelated with one another if there is physics going on. You could choose others. They'll make this a little bit worse, but they won't change it much because, for example, low northern variance and dipole asymmetry are the same thing essentially. And the worst it might be is if you multiplied the p-values of all those things. That would be the biggest the possible anomaly could be. That would be some number around 10 to the minus 10. Okay, and if instead you find somewhere around 10 to the minus 8, maybe a couple of 10 to the minus 8 p-value for this combination of anomalies, which is more than 5 sigma. So should you believe it? That's because it says that the universe is not statistically isotropic. Okay? Well, the first thing you might say if you're a hyper-Bayesian is you can't believe data without a model. Okay, now I just don't buy that. And if you do, that's up to you, but I think it's very hard to discover anything new if you adopt that approach, that philosophy. The other is you can say, well, you've cherry-picked, there's looked elsewhere penalties, you can always find anomalous statistics. And I'm happy to go into details of why I think that's a wrong argument. Let me start with go read a very nice little article by Louis Lyons in the CERN Courier about why do we use 5 sigma. Does anyone here really think we need 5 sigma of evidence that our realization is unlikely? Maybe there's someone. Anupam. Yeah. The real reason we use it is because we worry about look elsewhere effects, right? So now, maybe there's overwhelming look elsewhere effects in here. Maybe there's huge numbers of other statistics that we've all buried. But okay, the fact is that if you look at like the Planck exploration of this, you'll find that there's a surprisingly large fraction of simple statistics that you write down that end up being anomalous. Some of them tightly correlated with the ones that I talked about. Some of them not obviously correlated with the ones I talked about. So there are look elsewhere penalties, and there are also what I'll call look more closely rewards. They maybe balance each other. I actually don't think they do. For example, S1/2 of EE is like P of 10 to the minus 3. It's very low. So I don't think it's there. So the universe we observe does not appear to be a realization of a Gaussian random statistically isotropic process in a way that is extremely difficult to understand how it could arise from non-Gaussianity. And that's what I mean when I say the universe is not statistically isotropic. Now, of course, there are other things we should do. First thing is we should find a fundamental physics model. There's other things we can keep doing, and I'm happy to give a 2-hour talk about that. But what we really want is new models. And here is the list of new fundamental physics models known to explain all or most or several of the anomalies. It's currently an empty list. So lots of work for young people to do. That's great. You have to break statistical isotropy on scales that were causally disconnected until recently. Or you have to explain why there is a foreground that just happens to cancel what was there and give us what we see, or a foreground or a systematic that just happens to erase what we expect, what we should have seen, and instead gives us what we see. Here is something that is in our theory that does have statistical isotropy breaking on the right scales. Okay, and we're busy exploring it, and this is one of the reasons why. I won't explain topology to you. We've all had periodic boxes. That's a very simple example of topology. Here's one for S3. Here's one for H3. There's lots and lots and lots of things that have not been ruled out. That's an important thing to say. Okay. As one of the people that was involved, there's an amazing number of citizens who are involved in the early work, the late work in the late 90s and early 2000s, trying to look for the topology of the universe. Dick, Tarun, people who aren't here like Dimitri, Andrew Jaffe, Jana Levin, sort of citizens like Neil Cornish, lots and lots of people who were involved, and we didn't find it. And we thought, oh, we've ruled it out. But in fact, what we had done is ruled out some things. The Planck search, the Bayesian likelihood search, which is the best that approximately the best that you can do with all the Planck data, looked at a set of measures 0 in the parameter space. And we are trying at the moment, and it'll take us a few more years, to exhaustively look at the part of the parameter space for topology, at least for manifolds, that can be accessed by Planck. And we think we can do that with the advances in computer power and all of the analytic work that we've put in over the last 3 years. So, okay. So here's something that, the type of thing you'll see is that your correlation matrices are now no longer diagonal. In this case, they had lots of zeros, but in other cases they have none. Okay. But in summary, the CMB is not the realization of a Gaussian random statistically isotropic field in a way that seems to demand that the universe is not statistically isotropic. There are no proven models so far. It's very hard to get systematics to do this. It's very hard to get foregrounds to do this. Topology might do this. I'm not making any promises. I'd be very happy if it turns out to be right, but it may not be what causes this. So the cosmic orchestra may be playing a lambda CDM symphony, but somebody gave the bass and tuba the wrong score. They tried very hard to keep it quiet. They failed, and it's up to us to find an explanation. Right? And I had one more slide in my latest incarnation of this, which was to advertise a conference that you can come to that isn't about cosmic topology, but I'll circulate it. It's in March. It's in Jesi, Italy, at the end of August, beginning the end of August, beginning of September, and it's on large-scale computing in cosmology. So maybe I'll get it up there some other time. So anyway, thank you very much.
And that was exact 20 minutes. It's amazing. So we have time for a few questions.
Thanks, Glenn. So for the correlation function, I can take that correlation function and take the Legendre transform to get a power spectrum, right? That would then predict the correlation function we see. So are you saying that there's no way to do that like has a positive power spectrum, or like what can I do that with statistically isotropic sky? So I have the correlation function, which is weird given under CDM. So, well, why can't I just take that correlation function, take the Legendre transform, and then get a power spectrum that predicts that correlation function?
Okay, I changed my theory. I don't care what it is, and I predict the CLs that we see. And I predict the CLs that we see, which is maybe I can get that from a power spectrum. I don't care. Probably I can, right? But let's suppose I do that. Okay, and then I say, okay, let me have a universe that is a Gaussian realization of that. Okay, the ALMs won't be the C sub Ls, and this is a low L phenomenon in particular. And the deviation from the fact that we have cosmic variance will spoil the vanishing of C of theta. So you won't get a C of theta that's close to zero unless what you do is you make all the CLs small, really small, and then you will get a C of theta that's nearly zero, but you won't get CLs that look anything like the ones that we see. Does that make it?
I'll talk to you later.
Okay. Okay.
Hi, I think I'm next.
Oh, Nick.
So as you know, and as you pointed out, and Jan 11 just called me yesterday to say, oh, Starkman's still doing the same old stuff. She didn't say that. She's actually working on topology on very short scales. But we looked at this pretty hard with Shiji Wang in the 2012 kind of period, because I completely agree with you. These things stare you in the face, and you cannot ignore them. But my good friends like George Estathia would have said, I think he's changed a bit actually, is that it's all ultimately consistent with Gaussian random fields. So because we're dealing with things which are like a little over 2 sigma for each of the anomalies.
No, they're not a little over 2 sigma. They're 3 to 4 sigma.
When we did the stats, it was just a couple of sigma, and the issue was how do we get it up to be not 5, but at least over 4? So what you didn't mention is probably one of the most anomalous areas of the sky, which is the
cold spot.
Cold spot,
Yeah.
and that's another anomaly. And then there's the power spectrum dip, which
At L of 20, and is
and the issue is, unfortunately, there doesn't seem to be a grand unified explanation to tie them all together. And it's really unclear that a topology can do it. On the other hand, if something's going to go wrong, it's going to be on the large scales because those scales have only recently, relatively speaking, gone into the horizon. Now I'll get to the real issue here. The integral of C of theta squared is interesting, but what you would like to do is to actually get a better idea of the theory of variance. And the variance is basically associated with CC, but it's also got higher order corrections. And it would seem to me that that's a pretty important thing to do, and it doesn't seem to have been done in the subject, that you're actually trying to probe what is the higher order variances. You made a comment, which I didn't understand. I'm about finished. You made a comment, which I didn't understand, which was that in order to suppress the power, you slip it up into three, and then 3 goes to 4 and 4 goes to 5. Could you expand on that?
Right. So what I was trying to say there, and we have a paper that discusses it from quite a while back. So if you take this, for example, if you take C3 and above as what they are and ask, what value should C2 have had in order to make S1/2 as small as possible? And the answer is almost exactly the value it does have. That's very weird, right? So you vary C2, because C2 is, as we know, C2 is the one that is, quite low. And yet its value seems to have been selected in order to cancel the contributions to S1/2 to C of theta squared of the higher C's. This is almost true of C2 and C3. So if you take C4 and up as given, then C3 and C2 are almost minimize the possible value of S1/2. In other words, the observed value of C2 and C3 almost minimize it. So that's what I mean. And so that kind of correlation between the C sub L's can't happen if you just predict CLs, right? Because you'll predict CL. You could predict that. You could have your expected values of the CLs be those, but then you go out and make a realization and the actual values on the sky will not be those, and it'll spoil that cancellation.
Okay, we have to go to this discussions during a very quick question and a very quick question.
So all the anomalies you talked about, which I agree are fascinating, were based on the temperature map of the sky and the details of the temperature map. But it's not the only map we have. We have the polarization map. So the same anomalies there, or is there additional information in the polarization?
So one of the questions is, do you believe how well you believe the low, especially the low LEE maps? And the answer is, so if you believe the low LEE maps, then it turns out that the angular correlation of EE is on large scales is anomalously low. There's a paper by Natoli, Latanzi, and a bunch of other people from 2020, 2021, claiming a p-value of something like 10 to the minus 3, which Lloyd, you and I predicted shouldn't happen in lambda CDM. So that was a priori. We predicted that wouldn't happen unless there's a physical mechanism that does this, and then it's exactly what you expect. Now, the problem is, do we know tau well enough? Do you really try? Yeah. So that's the one that people have extracted, and that it seems to be reliable. Well, we're not sure it's reliable, and they don't know if it's reliable. So, okay.
Thanks.
Okay,
Ben.
that was quite a lively discussion. So we go into the next talk, which is by Tarun. So Tarun, you have it.
Okay, so I'll be echoing everyone's sentiment that it's a great experience to be back in CITA, and except for the people who are actually in CITA at this time, but most of us are delighted to be back at the reunion at 40. So let me begin by, okay. Oh, okay, I see. Sorry. Okay. So, of course, my connection to CETA happened, like many of you, with a offer letter and, a mail from Dick. And what I wanted to point out is I was doing my PhD in India in a new institute and had no clue where I would be going next. And this, for me, was a huge deal. I think I was the first Indian student to be picked up to CETA from. Oh, I'm Ghosh. I'm still Ghosh. Uh, the maybe at the banquet, but I just wanted to say that it was quite a big thing, and Dick being at IOCA many times helped build the cosmology as we see it in India, and I was glad Dick could come in December and see how big a community we are now. Okay, so let me just remind you that we have been extremely successful in this field of cosmic microwave background measurements, and my career almost spans exactly the same years from Kobe to now. And this is a plot from the Planck paper where they proudly show how much information has been added since the day of Kobe. And I think 3 into Moore's law, I'm not sure was in the paper or it's something that I picked up from Francois. But we have this standard cosmological model, and we are, at least have a base to stand on. And I see that as a big success. Okay. So let's now talk about what I want to mention. I mean, when I left CETA, of course, it was a revelation to me how far people had moved. And it was also clear that the field had amazing experts who would do this transition from, sort of hint of a concordance model to something established as lambda CDM being. And I knew that when I am in India as the only CMB person, I couldn't compete in a game. So I was looking and I was developing research programs which would probably be important after you have got your model. So something that the particle physicist faced beyond the standard model. You have a standard model, you get bored with it. Glenn clearly is, and others are. And so you want to see something new happening. And the fact that I spent this time in CETA, I was like a sponge. I absorbed a lot, didn't write that many papers, but I learned how to make robust measurements and robust statistics. So we developed a methodology for looking beyond the angular power spectrum, even for a Gaussian sky. And that immediately gives you access to all the things that Glenn mentioned, and additionally known effects. And that's very important to me because that tells you that your method is working. You have basically a Doppler boost, which can be measured very clearly, and weak lensing. And in the observational artifact, this last thing seems to be haunting us quite a bit, and I'll keep going back to that. So just to set the stage clearly, we are looking at statistically non-isotropic Gaussian models. I'm not saying there are no non-Gaussianities, but we are not looking for them. Essentially, the 2-point function is not rotationally symmetric. It's N1 and C of N1, N2 is not C of N1 dot N2. Okay, which again, as Glenn pointed out, is this SI violation. And this is straightforward in Fourier space. Your modes get correlated if you don't have the isometry. And, there were people thinking about this. Of course, this whole thing stems from work that I did with Dick and Dimitri in the context of something that Glenn mentioned about hunt for topology and of a particular kind, compact hyperbolic ones. So it's a picture from those years. I did manage to get the papers out, after I left. Dimitri says I'm probably one of the, what do you call, most successful collaborator, postdoc collaborator who managed to get the papers out in a couple of years after finishing in CITA. And this shows you plots that we were making of how the correlation function breaks down. So if you look at the bottom, you see what you expect in a statistically isotropic universe. The correlation function with respect to one point fixed at the pole just falls off smoothly. The contours are more or less circular. A mild breakdown, the contours are distorted. Radical breakdown, which happens in topology very readily. You have multiple imaging, you have, quite a bit of mess. And this is an example from compact hyperbolic universes. And this is the question that, again, I'm pointing to Jana's book, who made it very popular, spots, the universe as spots. So you could talk about is that spots as some beauty pattern or some ugly, effect. But the biggest problem is how do you measure a deviation from correlation, deviation from isotropy when you have only one CMB sky? And that was what was really the big challenge I felt was there. So then I started thinking of what are we doing when we measure the 2-point correlation function. You're essentially integrating over the rotation group. Right? So if I take a general correlation function, I integrate it over all rotation, the entire rotation group, I would produce the C of theta, right? And this is how you actually do it, more or less. But you know that the way you get Fourier transforms, there are ways to weigh such averages to get more information out. And and if you don't want to go for that, in the absence of statistical isotropy, you have no way to make any inference because there's only one number that you can measure per this thing, unless you know there's a pattern. And that's then match filtering. So that's not, that's a bit different. You need to know what you're looking for. So I'm very excited about this talk because in '99, CITA had a reunion meeting where I first time presented our approach in a conference. And I talked about this measure of statistical isotropy, which we call BiPS. It's bipolar power spectrum. It is a 4-point function, but this kappa L had the advantage that, if it was non-zero for any L greater than 0, it meant that there was a isotropy breakdown and it didn't worry about which direction. And this I like because in topology, you don't have to worry about then the orientation of the space. And that was what we did. So let me now talk further about it. So this was something, when I went back to India, I was lucky to get a very bright student, Amir Hajian, who is here. He was also a citizen. And we wrote this finally up. And basically, kappa L is essentially the same rotational average of the correlation function, but weighted by something called the characteristic function of the rotation group. Okay? And it spits out this kappa Ls. And I knew that much. And if I go back to this, not here, sorry. And then in the harmonic space, these are plots that we made, particularly Dimitri and I, which are covariance matrices of isotropic model. And the question that we were asking is, how do we grab all this information if statistical isotropy is violated and in a cogent fashion? And the idea was very simple. It's orbital angular momentum, total angular momentum representation in quantum mechanics. So you use this BipoSH spectra, which are, so in one way you have multiple spectra to measure, not just the angular power spectrum, but I can measure up to the exhaustion of information, a multiple number of spectra, and we should do that. And if they are consistent with, not consistent with 0, then there is something interesting to look for. And this is a very natural generalization of angular power spectrum. And I say this because one of the things which has always been pointed at about these anomaly claims is that, oh, it's an a posteriori statistics. To me, the bipolar power spectrum is as much just natural power spectrum measurement as you can think of. I can't think of anything, so it's a natural thing that you would do. You measure, you get it non-zero. I think the question of a posteriori statistics doesn't come. You didn't do some measurement earlier, and you're doing it now. Okay. So as I said, it's fairly well known in physics, this kind of thing, but it gives you access to a whole lot of possible phenomena. So the first one is the phenomenological model that Planck used to model this dipole modulation, the north-south asymmetry that Glenn referred to. You can take into account non-uniform variance, noise varying on the sky, weak lensing, beam non-circularity. And over years, I've been kind of developing this diagnostic as well as a way to look for any new effects. So few things that I should point out gave us a lot of encouragement. So WMAP actually used BipoSH for their 7-year release and saw this. If you notice the plot at the top left, there are high significance deviations when they look for the BipoSH at capital L, total angular momentum of 2. And this is distinctly a problem, right? And there was only one line devoted to it which said, oh, this must be some systematics. And I don't disagree with it, but it didn't say which one. And they pointed out that there was a mild variation in the 2 frequency bands. Again, I don't see that happening. But we actually tried to look for a model which will explain this. And what we did actually with a lot of my group members getting together is to take the WMAP beams, scan the sky like WMAP did, and computed the BipoSH and showed that you recover the signals. Okay, it took us more years to publish it than do it. I don't know why. But what we wanted to point out is a 0.2% effect in your beam distortion shows up at so many significance, so it's such a high significance. It was really amazing. And I thought that was the end of it because one of my students had a postdoc at JPL to solve the beam problem. And he reported that it has been solved, and I was busy with LIGO India, so I didn't pay attention. I thought Planck had no problems. But I'm back doing cosmology again, and I had some undergraduate students revisit, and I think Planck has a L equal to 2 effect in SMICA maps that is quite visible. And at this time, this is preliminary work. This is done by an undergraduate who is now at PI, starting his PhD, and one of my graduate students. And to me, it looks very clear, and we would do a Bayesian thing, try to get the eccentricity of the beam and things like that. But to me, it looks like this is happening. Okay. So next, I will talk about the dipole modulation. This, again, we did with Planck and gave a frequentist value of 6 in 1,000. Then we developed a method for a fully Bayesian analysis. And I wanted to point out that, instead of this effect dies off with L, and we fit a power law to it. Interestingly, for people in my generation before CMP physics, the fact that this index is -1, this effect falls off as 1 over L, is quite interesting because we know of physical effects which do. And we are going to do that. Then, as I said, it's reassuring that this method works. If you can measure the distortion in the CMB sky that happens when you're moving in a moving reference frame, which we are. So we are moving with respect to the CMB at 370 kilometers per second, which is a V/c of 10⁻³ Planck has the sensitivity to see it. In 2013, Douglas Scott developed a method to see it, but we used that to actually calibrate our method, and we saw it. And recently, there were some claims that the velocity is double with respect to the quasars. And when I said that we have seen it as a kinematic effect in Planck, I was told that statistical significance was just 3 for that. But I knew we could get it at 5 sigma, so we went for that, and we showed that at 5 sigma, you can recover the V by C just from distortions using Planck data. And again, we did a Bayes thing where we showed that a factor of 2 in the velocity is disfavored at 10 to the minus 11 odds ratio. And then I started going back to the real space understanding of BipoSH because, it's always very tempting to take ALMs because all the stuff is set up and calculate the BipoSH. But, so we've been trying to understand how can the information beyond the angular power spectrum be kept in a very compact way. And this is some recent work where we showed that, of course, for C of theta, you are on a circle. If you add a sphere to it, you can represent an isotropic thing in full detail. So you can completely map this space in this representation. So I won't get into that, but that's a recent paper with one of my students and an undergraduate student. And I'm very excited because now we are almost going back to the beginning. And it's interesting that this slides I found just a few days before I came, and I was sharing it with my postdoc, whom I told that I had given exactly the recipe for calculating kappa L, but I don't remember it. Okay, and I rediscovered that whole thing. And also the fact that I had recognized that it can be expanded in BipoSH. But this was 1999. And this postdoc of mine comes from a very theory-minded guy. And he developed entirely the maths, which leads to the BipoSH, which are basically correlations averaged with the diagonal terms of the Wigner matrix. Okay. And again, that allows you to represent it. So just like I said, you have copies of CLs at larger L. Not copies, sorry, versions of angular power spectrum. Here you have a set of correlation functions, which are, each of them are isotropic, just C of thetas, but with some label. And you get that whole bunch and you're done. And the advantage there I see is for incomplete sky, maybe that's a better way to do it. For polarization, it may help. Delensing, it may help. But we have yet to explore it. But I think that we are put the whole thing on a much more, stronger footing, and we can move forward. We have all the, tools for doing the fully Bayesian thing, so that's not a problem. But understanding is important, and that's where we are. We showed that you can measure things in real space, and I won't. Okay. So let me just tell you where I'm heading with this. I think CMB analysis should be done in the BipoSH space. Okay, not just because we were talking about it. It's the natural space to do it because, except for the signal, nothing is believed to be statistically isotropic. The noise is not, the foreground residuals are not, and any other effect you can think of, break it down. So the correlation function has signal, noise, and foregrounds. If you want to deal with them, they are diagonal in different bases. BipoSH is one basis where you can put them all together. And I'm hoping that we can develop this comprehensive studies with this. And since there's nothing coming up after full sky, after Planck soon, I think I'll have the time to do that. Thank you so much.
Tarun, since we're really running short of time, we'll have like one question. And Rein, if you can. Okay, Glenn.
Hi, Tarun. Really lovely talk. I mean, I've been really interested in what you're doing with this. One of the things we've tried to struggle with is, the kappa Ls are a way of summarizing the information in the BipoSHs. And for example, you mentioned that as L gets large, the significance of the dipole modulation goes away, right? And you would see that you could see that with kappa Ls, I think. But on the other hand, the direction, if you ask what's the direction of the dipole you extract at higher and higher Ls from the modulation dipole, that direction stays remarkably consistent out to I think it's these days out to nearly L of 3000. Okay. Even though the amplitude is no longer significant. And
Right.
so how would you end up trying to see that kind of information from the BipoSH? It's in there.
Oh, the BipoSH has the small L's also, right? So it's a capital LM and L1, L2 are just, L and L plus 1 or L plus 2.
No. I know that it's absolutely in the it's
So you
absolutely
can
in
show
the
that it is dying off.
Right.
Yeah,
Right.
but that part you can get, and if you're asking for the physics, there are multiple effects which fall off as 1 over L. So it means that although the primordial CMB may be isotropic, the 1 over L terms that add to it are not, and that would be interesting if that's what you asked.
Okay, thanks, Tarun. Let's move on to the next talk.
So I'm finding myself in a session where most of the talks were about the universe on global scales, the cosmic microwave background. That's not what I'm going to talk about. I'm going to talk about the cosmic web, something on much smaller scales. The common denominator, I think, here is big, because we are all doing this because of us being here in Toronto at CITA, working on various aspects of interest of DIG. So I'm more going to talk about the cosmic web, the pattern that matter, gas, galaxies are basically outlining on scales of a few up to hundreds of megaparsecs. What you see on the background is basically a reconstruction, a constrained reconstruction based on 2 mass of the Piscis-Perseus chain, the largest filament in the local universe. What I particularly want to talk about is the forces and the tides that are basically resulting the cosmic web. How do we get to these filaments? And in particular, what kind of role do they play? And in particular, the empty regions, the voids. In how far are they important? Do they play any role? I mean, they are rather underdense, so they do not contain a lot of matter. So you could say, I don't care that much. Is that really true? We will see that's not true. They are actually pretty important in putting up the pattern of the cosmic web. But the question is also another one. If you look at the voids, you could say they are expanding underdense regions. So that's what we basically have to concentrate on. Well, nowadays, voids have actually become a very interesting probe of global cosmology. They're very sensitive to, for example, dark energy or deviations from general relativity or anything like that. So they've become interesting probes in their properties. A lot of that is based on the assumption they are actually expanding because of their own underdensity. But in how far are their dynamics actually only dependent on themselves or influenced by the environment? To do that, we actually set up a statistical inventory of the force fields and the tidal fields in the cosmic web. on the basis of a, let me see, does it work? Oh, it doesn't work. Oh, it's the bottom one. Ah, yeah. On the basis of a dissection of simulations in this way of the cosmic web. Here you have basically an outline of a typical filamentary pattern in the cosmic mass distribution. Clearly visible is the huge artery, but you know, we're talking not about a pattern on a particular scale, it's actually a multi-scale pattern. So here we see basically the filamentary outline. Some of this is the main artery forming there, and when it gets towards the cluster nodes, they can reach overdensities of around 100 to even 1,000 of the average. But you also have the small tendrils sticking right into the underdense regions, and they may even be underdense. So you also have to take that into account. So how we are going to do that? Now here is just to give you an impression of what is happening. Yesterday we saw Simon talk about the very local universe. Well, here you see an overall pattern, and you see clearly the imprint of voids. You see the stuff streaming out of the voids, but you see it becomes very interesting when you get near the filaments. When you get near the filaments, you get basically clear shear flows, as you see over here, clear shear patterns. So you see an outflow divergent pattern coming from the voids. You see the shear patterns basically tying in with the filaments and the walls. And the question is, who is influencing what? Now that question cannot be decoupled from location. It very much depends on the location. You cannot say voids do not play any role. You ask the question, where do they play a role? Is it in the overdense regions? How is it in the underdense regions themselves? So we actually also looked as a function of environment. So how are we gonna put this on? Now, starting with basically the main question, what turns out to be the case is that filaments are dynamically the dominant component of the universe. That is to be understood because around 50% of the dark matter, also around of gas, and also of the galaxies are living in filaments. But when we look at the overall pattern of the cosmic web, it turns out that the voids play an enormous role in placing everything into place. So that's going to be the conclusion, and I will sketch how I got basically into that conclusion. Everything is built on basically an objective classification of the mass distribution in a distinct pattern of filaments, walls, nodes, voids, and etc. And we wanted to do that, and we want to do that in a way that is not only saying there is where you have a filament, but what kind of regions or which mass elements belong to filaments, which ones belong to voids, which ones belong to the walls. Because when we can do that, we can actually do a dynamical treatment of their influence. We also have to take into account the fact that they are multi-scale. So you have actually structures on very large scales, you have structures on small scales. To this end, we developed, over the past decades, a machinery called MMF Nexus multi-scale morphology filter. It's actually stemming from medical research. That's where we borrowed it from, because basically in medicine, they of course have to deal with CT scans, and they have to look for all kinds of things of interest, whether they're interested in arteries or some suspicious lumps and etc. How do they pick them up? A medical doctor cannot, of course, look over thousands of scans and see that's wrong. So actually, in the 90s, they developed a machinery where they basically took a three-dimensional image and gave it an extra dimension and called that scale space. That extra dimension is scale. So here you see basically what scale space is. Then subsequently, in a geometric way, locally, you determine in what kind of structure you live. If you live in a flattened entity, you basically look at the local geometry, you can say that's a wall. And a filament when it's more elongated, and etc. And then subsequently, you wonder over the various scales, which at that location is the dominant component. So when you, for example, are embedded on a 10 megaparsec wall, it could be that at 1 megaparsec, you're in a more strong string within the wall. So the formalism is basically selecting which is the preferred scale. So that's what we called the multi-scale morphology filter. There's a whole range of other issues involved, because you might ask, do you look at the density field, or are you looking at the gravitational field or the divergence in the flow? You can basically choose whatever you want. Most of the time we look at the density scale. So what you get is, for example, here, the filamentary pattern for the various versions that we had. So, for example, the top one, you have the density field. Nexus Plus is our preferred one because it really looks at the mass distribution over a very fine grid of scales. So it feels basically the small scale filaments and the large ones. But you could also look at the shear in the velocity field or in the tidal field. They pick out actually the larger patterns, while the density field is more sensitive to the small patterns. You can, of course, also get the membranes, the walls that are tied into that, and they're connected. You can investigate the connection to all of these. And in the end, you get a sort of a multi-scale map where you have, like here, you have the filaments, and you see basically in color grading which scale is dominating there locally. So you could see, for example, the main arteries, the very thick ones in red, they are the filamentary arms of the clusters, and the small bluish ones are the ones more living in voids. So we use this thing for an inventory of the cosmic web. So we took a simulation and we looked at the gravitational field, right? So at each location, you look at the gravitational field. But then we dissected it with nexus into the underdense regions, filamentary regions, wall-like regions, and we asked at every location, is your gravity, how much of your gravity is due to filaments, how much is due to the voids, how much is due to the walls? And in this way, we could do a sort of objective inventory of the thing, right? So here you see basically this section into filaments, the void regions, the walls, cluster nodes, and etc. And then the resulting force field is like this. So you see now it's the force field, the total force field is of course the sum of these things. So it's not scaled, by the way. We basically fitted everything in. So the filamentary vectors would by far be the largest ones, and then the void ones would be smaller. So it's all a bit rescaled in that sense. But you see the overall pattern. You see that filaments have a very coherent pattern of forces over the entire volume. But when you look at the voids, you constantly see these very nice, almost spherical-like divergent flows out of these things. And you can recognize actually when you look back the pattern of the cosmic web in the distribution of the voids, less so in that of the filaments, right? So when we then subsequently looked at the force field, then we get the maps of the amplitude. And here you basically see it in the right scale. So of course the nodes are extremely strong, but very localized, right? So they are these peaks standing out with a mass density of around 1000 that they dominate their environment very much. But it's rather limited. The voids, on the other hand, they are huge stretches of space. 75% of the cosmic volume belongs to voids. So the interior of voids is basically feeling much more that push, effective push out of the interior. While when we look at the top left hand, it's the force field of the filaments that is clearly standing out as the strongest part of this order. So how does this work out in terms of statistics? Now, in terms of statistics, when you make basically the PDF at every location, you're going to ask which percentage of your force is due to filament, which percentage is due to the voids, which to the cluster. You basically get that middle graph that you see over here. And you see, yes, in purple, the filaments are the guys dominating everything. So wherever you are, filaments are basically the most dominant component. But don't underestimate the voids. You see in orange that the voids, on average, contribute something like 20% of the force over quite a volume, including even in the filaments and the walls, right? So they are actually dynamically important part of the component. You could, of course, also distinguish by region. You could say, if I live in a void, how much is due to myself, to the voids, how much is due to the filaments? That, of course, you see in the top left-hand one. And you see that also in the voids. The filaments have an enormous dynamical impact, but they themselves are very important too. This is important, though, in light of the attempt to use the voids as precision cosmology probes. If you don't take into account that their own flow field in the voids is heavily dominated by the environment, you may miss out on, or you may basically overinterpret their outflow pattern that you see in those voids. When you go to the filaments, I mean, filaments don't care that much about their environment, although even in the filaments, the voids have some influence. So you might even see, you know, galaxies having some outflow part, even in the outskirts of the filaments. Although when you look in detail, when we looked in detail, you see basically the voids having an influence down up to the filaments, and then very soon their influence drops out of it. So they have very localized influence in that sense, right? They influence themselves and their environment, but you don't feel them further on. So in view of the time, there's another part of, this is basically some of the case studies. So we basically looked, for example, in one particular void, this is stretching. So you see the void force itself, that's the outflow pattern. But if you look at the top left-hand side, you see that in the void, you feel enormously the forces imparted by the clusters and the filaments around it. You cannot see the voids as isolated objects. Right? So we did the same analysis. In view of the time, I won't go into detail. We did the same analysis with the tidal field. And the tidal field is, of course, a very interesting part of the whole dynamical story. The shaping of the walls and the shaping of the filaments is all due to the tidal forces. And the close connection between tidal force and mass distribution, you clearly see, for example, here, when you look at this pattern in a filament, and we basically determined the tidal force field, and we looked at the directions where the force is basically compressing, and put a little bar over there. From weak lensing studies, you see the same thing. And you see the enormous bird nest of the cluster over there, and then you see the very coherent pattern of the tidal force along the filament. So there's a clear close connection between those things. Right? So we determined, in the same way as we did the gravitational force field, the tidal force tensor at every location, and we dissected it by walls, filaments, voids, etc., like that. In that sense, it's interesting in the light of the discussions on the cosmic microwave background and the Gaussian noise that we started with, you may wonder, where is the cosmic web then coming from, right? Well, it's coming from basically the deformation flow set into motion by the tidal forces of the mass distribution. If you actually take the Gaussian field Here is a Gaussian field. You see the top left-hand, bottom left-hand plot. That's a clear realization of the density field. But if you plot the corresponding eigenvalues of the tidal force field, you see that actually already in the primordial distribution, the cosmic web is there, right? Because it's basically the force field that's going to shape the filaments and the walls and stuff like that. So we set up this calculation, and we basically, as we did for the force field, calculated the influence on the tidal force, and this is the amplitude of the tidal force, but you can do various things, the anisotropy of the force field, etc. You see that clearly the filaments are very strong. But the most interesting one I personally found is what the voids are doing. They have this beautiful web-like pattern pushing on the entire volume. Of course, nodes and walls are basically only a minor reflection of the filaments, but in particular, it's the voids versus the filaments. There you see a clear distinction. The filaments are strong, also in tidal forces, but the overall pattern is the voids, right? So it's as if they actually push everything into place. So here you see basically some tidal forces around voids. They are typically, and here is some of the statistics. And only repeating what we did before, what you see is that the filaments, the purple, is the strongest, the most outstanding, but the voids here are pretty important elements of the entire force inventory. So I think in view of the time, we will keep it to this. Thank you very much.
Thank you. Thanks a lot. We are already running pretty late. So if you want a longer time in the coffee, we have to keep the questions short. So maybe one question. There.
Very nice, Rein. I'm really pleased to see that you were one stream leading out from the void of CITA, but then there was the whole Pichon-Pagassian stream. So lots of people doing cosmic web. But the question I have is that you emphasized here the Hessian and then the tidal field. There's another field, which is actually a rank 4 tensor, which is the dij dkdl of the gravitational potential, which is more like curvature in the GR sense. Have you ever thought of fooling around with those extra indices?
Not exactly. We are the line of in choose by web. So there are mass dependence when you look at the space when they are small scale reality or small relations or large galaxies. And then of course you get a short perfect, the migration tensor and the firing tensor. So that's what we are. But that's not the thing I'm looking at. What we are is present.
Okay. Since we're running late, we should stop over here and move out for coffee, and maybe we'll come back 10 minutes later at 11:10. So we have